Okay. Okay, so 60 people have joined in already. I'll just go ahead and start, and more people will keep filling in later. So, hello everyone. Good evening, and thanks for joining. Thanks for taking out the time and to join this session today. For those of you who are joining a hash include session for the first time and wondering what it is, it's a forum run by Gojek for discussions on tech to host people like Karthik today. Learn from them, build a community to discuss interesting tech. I'll just give a quick intro about Karthik as well and hand it over to him. So Karthik is one of the original database engineers, was one of the original database engineers at Facebook, responsible for building distributed databases, including Cassandra and HBase. He is currently the co-founder and CTO of the company Yugabyte, and it's a fully open source distributed SQL database for building cloud native and geo-distributed applications. So over to you, Karthik. Please feel free to fill in where I have missed out. And yeah.
Yeah, no, thanks a lot for the intro, Ayush, and also thanks a lot, Rajiv, for inviting me to give this talk, and thanks everyone for your time. So maybe we can just get started. I think Ayush already gave you guys a good background, but some of the interesting parts, like myself and my other two co-founders, we met at Facebook, and we originally worked on Apache Cassandra. Like this was back in 2007, and open source databases were not popular back then, and nor were distributed databases very popular back then. Like Google had Bigtable, and there weren't too many others. Like, and Amazon had Dynamo, like the original version of Dynamo, and like they put out the Dynamo paper. So we were trying to solve the big data problem for Facebook, and ended up building Apache Cassandra, or ended up building a database which got open source to become what is Apache Cassandra today. Subsequently, we worked on HBase and putting it into production for some very large use cases at Facebook. So like the first use case was Facebook Messages, where we started out with, I think about like 20 billion messages a day being sent across users, and we put that on top of HBase. We were also the team that was taking care of running this cluster in production. So we're kind of bringing all of that experience together and combining it with relational technology like PostgreSQL, and trying to see how we can build a cloud native version of PostgreSQL. So that's really what this is about. And we're going to talk about the architecture and our path to getting there. Okay, so just a quick intro for those of you who may or may not have heard of Yugabyte. Yugabyte is a distributed SQL database. We'll look at what distributed SQL is in the next slide, but it's a distributed SQL database with focus on high performance or low latency. So it's written in C++ from ground up. It is a cloud native database that can run natively inside Kubernetes, VMs, or bare metal. So you can truly run it in any cloud. It does not have any external dependencies. And it is an open source, it's a fully open source database under Apache 2.0, so which is very similar to PostgreSQL itself, which is open sourced under a very permissive license. So the entire database, including all of the enterprise features, security, backups, all of that stuff is completely open. Okay, and just a quick piece of info on what is distributed SQL, like just to define it. Like people have a notion of what it means when they hear that phrase, but distributed SQL is a SQL database that also offers resilience, which is like tolerating failures automatically without any human interventions, and scalability. So just add more machines in order to scale out, and geographic distribution. So whether you're talking in a modern cloud, a multi-zone environment, or a multi-region or multi-cloud hybrid, all of these get covered by the geographic distribution bucket. Okay, so let's keep going. At a high level, these are the architectural layers of Yugabyte. There is a query layer, which is built to be a pluggable query layer. So Yugabyte can actually talk multiple APIs. And there is a storage layer called DocDB. The query layer reuses PostgreSQL, which is inspired by Amazon Aurora, because Aurora reuses it offers everything that PostgreSQL or MySQL have. This is a similar architecture, but the lower half is inspired by Google Spanner, unlike Aurora, where you can actually do shared nothing distributed transactions, fault tolerance, so on and so forth. Okay. Now, how did we do this? I just want to lay out a high level plan of how we did it and then go into the architectural details so everybody has an understanding of how this really works, right? So if you take a single node PostgreSQL, right, at a very, very high level, you can kind of split the architecture of Postgres into two parts. There is a query layer for Postgres, which receives the query, and then it does all the security checks and authenticates the client, and it does analyze the query. It rewrites the query into how you want to actually execute it and comes up with a query plan and then executes the query plan and gives you the result, right? This is the upper half of the database. And there's a lower half, which is the storage half, which actually, like suppose the query was doing an insert, right? When you execute it, you will want to make some changes on disk and keep some changes in memory and put something into a write-ahead log. That's done by the lower half of Postgres, which we'll call the Postgres storage layer, right? Obviously, they work really hand in hand. So in reality, it's not going to look as pretty as there's a box up, there's a box down, there's two different things. It's like really intermingled, but logically we can separate it this way. Now, the way Yugabyte then does this is we reuse the upper half of Postgres because we tried to rewrite it and then we learned the hard way after 6 months of effort that this is not something that's going to happen anytime soon because Postgres is represents 30 years of development in the query layer. It is incredibly feature rich and building these features one by one is going to take more than 10 years, even if we really focus on just what Postgres is doing, right? So we said we need a better way, like a more engineering friendly way. So we said we'll reuse the query layer and we're going to replace the storage layer with a distributed storage layer, which is the storage layer of YugabyteDB, and it's called DocDB, right? So we'll dive into what DocDB does and all of that in detail. But at a high level, this is step one, where you take any one Postgres layer, now you're able to talk to multiple nodes, right? Now, if you keep doing this, you will realize, if you only keep doing step one, you'll realize that a query that hits one node, for example, can do like the sum of all values in a column or the maximum value, like select max of any of the values in a column, right? And this would only hit a single node and it would read the entire database worth of data into a single node in order to compute the max, which can be really inefficient, right? So step two was, how can you take subplans of this query that Postgres generates and kind of push them into multiple nodes, right? So you may want, and the set of nodes really depends on the query. Like you may do a range query, you may do like a straight up max query across all, but you would need like even a count star, for example, of all the rows in your table would need to be parallelized, right? Because as your amount of data keeps increasing, you definitely need that parallelism, right? So second step was to what we call push down sub operations in SQL or subtree of the execution tree into each of the nodes in order to improve performance. Okay, and then the third thing is to enhance the optimizer. So if you now stop at this point, you will now have a query plan that's generated for a single node, which is executed reasonably efficiently by pushing it down to the various nodes, right? But that may not be the best because transferring data across the network could represent more latency in execution than moving the code to where the data is. So if you actually change the plan in order to minimize data shuffle and move even if the plan looks suboptimal for a single node, it's more optimal in a distributed system. So this is stage 3 or step 3, which is like enhancing the optimizer in order to kind of inherently understand network costs, table sizes, table splits, so on and so forth, right? Now, these steps are not done ever. Like it's as much done as, say, for example, even a PostgreSQL is still evolving, right? So these steps always evolve. And these steps are kind of in the order of their maturity, right? The first step is most mature, the second step is a little less, and the third step is the least mature, but they're all making simultaneous progress, right? That's the way you kind of build a holistic system. So that's just an overview of the different areas. We're only going to look at step 1 for this talk, right? Because step 2 and step 3 kind of layer on top. And if you get the step 1 fundamentals, which is really about moving it to a Google Spanner-like system, then we can easily understand the other parts. Okay, so let's look at the design goals. What should the database support? This was the first question that we had to ask. We kind of looked at all of the relational databases, MySQL, PostgreSQL. We looked at what Spanner does, what Aurora does. Everything was out there before we started to build Yugabyte back in early 2016, right? So in order to answer this, we kind of analyze, if you just analyze what these two databases do, PostgreSQL and Google Spanner, you'll see that PostgreSQL, of course, supports the PostgreSQL query API, which is the wire protocol. And Google Spanner is its own SQL flavor. right? Like, so it's not PostgreSQL, it's a new flavor of SQL. The disadvantage of such a new flavor, and it's okay for Google Spanner, but it's definitely not okay for a new open source database that, you know, would hopefully help a lot of people, is because you have to learn everything anew. You have to build your ecosystem, your ORMs has to be built. So you have to build a lot of stuff, right? So we said, we're going to stick to Postgres completely. We speak the way Postgres speaks, right? The second thing is the set of features supported, which is like if you want, for example, a stored procedure or a trigger, or you want a partial index or an expression-based index or column level security. These are very complex features. And we said we're going to retain all of these because as app developers, we may not sometimes realize what level of depth we're using. It may just be that you throw up a GraphQL and it talks to the database below. And you think, okay, I'm not really using anything. I'm just doing selects. But that framework is really doing a lot of stuff underneath, right? It may be creating custom operators, custom functions. It may be doing all sorts of crazy things underneath. And so the support will then get lost and you'd have to rebuild, somebody would have to rebuild all of those bindings again. And then of course, you know, fault tolerance, scalability, and distributed transactions. It's not what Postgres was built for. It's a single node database. So those are things that Spanner was clearly built for. And if you look at geographic distribution, Postgres can do asynchronous replication, Spanner can do synchronous replication, right? It's kind of, those are the two different design points. So you can apply a transaction on one node and get it asynchronously replicated to another node. You can simultaneously apply a different transaction on the other node and get it replicated back. So you can do bidirectional async as well with Postgres. Of course, with Spanner, you cannot, right? Like, so it's more like synchronous replication in a cluster that spans all of those geographies. So what did we do? We said, like, the first thing that we want to do is like in Yugabyte, we wanted to retain everything in Postgres and all of the stuff that's unique to Google Spanner. So that's what we want to mix. And as far as global transactional replication semantics go, we wanted to do both synchronous and asynchronous because it's pretty useful in a lot of scenarios, right? So that's our design compatibility matrix. Okay, so those are the aspects that we picked from each of the databases. Okay, so now that we know what we're building with the database, the next question was, what kind of RDBMS features should we support, right? Like, okay, so these are just like high level, like we're saying, okay, it supports data types and it supports queries and it supports like indexes and constraints, but what are the things we should support, right? So over time, we've been very happy. We kind of threw away 6 months of effort of rewriting and went back to reusing PostgreSQL. We're like super happy with that because here are a long list of features that Yugabyte today supports already, right? Like you can test it out, it's in the open source. And you can just install the database on your laptop and try it out. But anyway, so most of the operators, expressions, built-ins, partial indexes, table functions, stored procedures, like, you know, a long list of really complex RDBMS features that are supported by Yugabyte thanks to the reuse of Postgres. And what makes it interesting is that the list is so long and so complicated that we feel like rebuilding this is going to be very difficult, both from a functional or design spec point of view, like just coming up with the right usability for all of these complex features, as well as being able to support them in a timely fashion with, you know, high quality code and testing and all of that is really hard, right? So we're really attributing this to the reuse of PostgreSQL. And again, most of the distributed SQL databases, Google Spanner included, do not support, I don't think they support any of the features that we listed out in the previous slide, right? So if you look at your frameworks and your applications that you're building, invariably, it's not every application or every query or every microservice that will need everything. But over time, you start needing a bunch of these features. And even if you need it in 2 or 3 places, you either have to go find a different database, or you'd have to find really complex workarounds on the application layer. And each person will implement this paradigm in a different way, right? So, okay, so how did we do this? So how did we really reuse PostgreSQL, right? Like, now here's a slightly more deeper view into Postgres. We said we'll split it into the query layer and then the storage layer, right? So here's a slightly magnified view of that. The upper half, which is the postmaster, which does authentication, authorization, rewriter, planner, executor, optimizer, all of this stuff represents what we're calling the upper half, or the query portion of the PostgreSQL database. And the lower half is the one that writes the write-ahead log, background writer, flusher, vacuum system, keep making sure the data on disk is laid out well, all of that stuff, right? That's the lower half, which interfaces with the disk, right? So we wanted to reuse the query layer of Postgres, which is the top portion, and we wanted to replace the lower portion of of PostgreSQL, including the disk with multiple disks and multiple nodes, right? So it kind of brings in YugabyteDB, at least the storage portion of YugabyteDB on multiple nodes, and this system on top should be able to talk to it. Now, it's very great, it's very easy in a diagram, right? But in reality, that's not the case because everything is kind of wired to talk to in-memory structures, which are meant to flush to disk. So it's kind of like really surgical in order to cut it out at that layer. So we needed a bunch of changes to every layer, a lot of layers. So the planner, executor, optimizer mainly. The upper half is still the same of the query layer, which is the postmaster and rewriter are relatively the same. There's still a notion of dealing with distributed caching because Postgres can always look up, it's like, for example, if you look at authentication, right? Postgres can always look up who the users are locally and invalidate those users in the cache locally and you're done, right? But it's not so in multiple nodes when you can attach to any node and connect and you should still perform the right authentication. So there's still other changes, but this is just a high level overview, right? So anyway, so we had to change all of this stuff. And so what that really transforms Postgres into is a stateless Postgres upper half with a DocDB storage level lower half, right? And we'll look at how DocDB works in a bit. I'm just going to go over the high level principles of what DocDB does, and we'll see how it really works. So the stateless Postgres upper half means a client app can connect to any node, right? Usually all nodes are the same. It doesn't really matter. So you connect to any node and internally it's going to route and replicate and do all of the right things by interfacing with the right DocDB layer below, right? And if you lose a node, you can always connect to a different node, or if you are connected to a different node, you don't care from the Postgres layer because it's a stateless layer. You just like connect to a different guy. You just round robin to a new person. And on the DocDB side, it can inherently survive faults because it's built like Google Spanner in order to survive faults. One of the core principles of DocDB is that it's highly available. So it's a consistent and partition tolerant database. So it's a CP database with HA, not perfect HA. So what does HA mean? It means that on a failure, a new node can take its spot in about a few seconds, like 3 seconds in a public cloud multi-zone deployment, right? So in 3 seconds, you have multiple other nodes serving data. So that means if you set your timeouts right in the app and therefore the stateless Postgres layer, you will be able to retry and get a new node who's a substitute for this node who's now assumed leadership over shards of data in the cluster and be able to make progress on your statement or operation. Right? Okay, so with that overview, that brings us to the next portion, which is like, I think in this diagram, if you think about it, the key part that we have not yet touched on is how does the failover work, which needs replication, and how is the data spread for a table across multiple nodes? So how does sharding work and how does replication work, right? So that's very similar to Google Spanner, but we're going to look at it in this section. Okay. So first thing about sharding is that every table is implicitly sharded. A user doesn't need to know. You can choose to not shard it, that's fine. These are explicit controls. You can choose to specify how many shards there are. But by default, most tables are implicitly sharded. And there's multiple sharding strategies, but we'll go to that later. In the most simple explanation of what a shard is a group of rows in the table. So if you have like, say, 100,000 rows in the table, you may want to create 100 shards with 1,000 rows each, right? Again, how you pick these rows is your sharding strategy, but somehow you can split these, right? And these shards, if they grow big, can split over time with dynamically and so on and so forth, right? But like, at a high level, this is what sharding is. Now that you have split your data into 100 of these shards, each shard is replicated across multiple nodes. Right? So that's the granularity at which Yugabyte replicates data. So every shard is now put on 3 nodes, and it uses a consensus protocol called Raft, which we'll look at in a second. But the point is the data for each of these shards, every shard in Yugabyte is called a tablet. So it's like, it's again, the name borrowed from Spanner. Tablet, it just stands for a small table, right? Like sort of tablet. So anyways, so Raft is used in order to replicate data. Oops, I want to go back, yeah. So this is the consensus algorithm in order to replicate the data of each shard across the 3 nodes, and Raft ensures high consistency of data. Right? In Raft, you first elect a leader. So the node on top here becomes the leader, and then all writes are processed by the leader. And the writes have to be sent to a majority of nodes, to all of the nodes that are replicas, but you wait to hear back from a majority. And then you know that the data is durably replicated and you can actually survive failures. And if a node fails, a new leader is elected, which happens in 3 seconds. And this is just one tablet view, right? Now you have to kind of put the view across all the tablets to say, hey, this is how the whole database is laid out. Okay. The interesting thing that we had to do with respect to Raft is that Raft says in order to serve a read, you should also do a round trip replicate to each of the nodes to establish you're still the leader before you serve the read. So after you get the read request, before you serve the read, you need to ensure you're the leader, right? And that means you have to reach a majority of nodes. And if you're doing a multi-region deployment, this could really be slow. And this could also increase network overhead and CPU, right? And high read throughput system. So which is highly undesirable. So the way Yugabyte gets around this, because high performance is like a core important thing to Yugabyte, is it uses something called leader leases. I think what this diagram simply says in a, I'm just going to give the layman version of the diagram, is that like node B, let's say, becomes a leader in Yugabyte across 3 nodes for a tablet, then node B will replicate using Raft leader lease interval. So it will say, hey, for the next 2 seconds, I'm the leader. Nobody else can become the leader. So all of you guys who get this and accept it, because you're a part of Raft and you've elected me the leader, you give me the promise that for 2 seconds, you will not, from 2 seconds from now, from whenever you receive this message, you will never assume leadership. Right? And they say, okay, and they agree. And so once they get this message, they say, I'll start my clock now. And the node B has obviously already started its 2-second clock, and it keeps going forward. And Raft relies on heartbeat exchanges. So every heartbeat exchange, it renews its lease. It says, give me 2 more seconds, give me 2 more seconds. It keeps doing that. So that means that since it takes 3 seconds for the failover to get detected and a new leader to take over, you're kind of okay, because once a new guy becomes the leader, he can assume leadership. But you've kind of carved out this 2-second window where nobody else can become the leader, so you can just serve reads from the leader. You don't need to do this replicate to majority and wait for everybody to answer. So that kind of improves the performance a lot. Okay. Okay, so as a result of all of that, the reads are handled directly by the leader, and this is where leader leases come in for performance. I mean, there's a number of other improvements we did for performance of Raft, but I'm just going to gloss. I mean, I'm going to skip that portion. Again, happy to go into details if people are interested. Okay, so with this kind of a view, right? Like, let's look at how a create table works, right? So we said there are tables in the .db layer which are sharded and replicated and fault tolerant, and then the SQL layer is just the Postgres's upper half. Now, in Postgres, you actually create tables, right? So what is the binding? Every user table maps to a separate .db table, which is sharded, replicated, all of that stuff. The system tables of Postgres, right? I don't know if anybody knows Postgres well enough. Like, I usually ask this as a question to the audience, but I don't know if people want to take a guess on how many system tables PostgreSQL has. Well, I don't know what number you'd come up with, but the real answer is about 279, right? There's 279 tables and relations. And the first version of Yugabyte we did could barely run because it couldn't support 279 sharded tables on top of its own system. So it could barely support system catalog. So we said, like, hey, this is not really a good option, because every table has like a handful of rows, right? So we kind of put all of these tables into a single tablet because there's barely any data, right? And that tablet is replicated. So we call this co-location, or a table group, right? So we kind of put this table group into one tablet. But all of the system catalogs are a special table that are replicated and highly available. And if you do, like, every .db table, .db is a document database, right? So every table has the same schema. It's key to document, right? But the layer above, which is the Postgres layer, really enforces that schema to say, hey, what column is what, and so on, right? So now all of your columns are mapped to attribute documents inside attribute values inside the document. So a row becomes a document. The primary key of the row becomes the primary key of the .db layer. So this is how it looks. When the system comes up, you already have 3 tablets, and the circles which are filled in and in bold are the tablet leaders, and the ones in dotted cylinders below, right, like right here, these are the followers. So you already have 1 tablet of the system catalog running and replicated. Now, when you create a table, this is what really happens. Irrespective of which node receives it, it's going to find the leader of the system catalog internally, and it's going to say, hey, this is the table that's being created. Obviously, it's not a simple record. There's a lot of operations when you create a table, because a table itself can have constraints, it can have default values, index, it can have a lot of stuff that are going in, but simplistic view. Now that tablet system catalog reader replicates the data to 2 other nodes, because we want that also to be highly available and fault tolerant. So once this is done, then the next thing that happens is to create the tablets of the table that are just being created. So in this example, we created 3 tablets, T1, T2, T3, with 3 replicas each, right? And you could do more or less. I mean, this is just showing a 3-node example, but you could have more nodes, and therefore you want to place it in such a way that your tablets are evenly balanced, your tablet leaders are balanced. So there's just a lot of balancing that goes on internally. But anyways, this is the simple view, right? Now, when you insert data, the primary key columns of your table will map to the document key. The rows of like the PostgreSQL table will map to the document. The non-primary key columns will map to the document itself with attribute values. If you create a table without a primary key, it just assigns a logical row ID internally, right? So you still get a primary key implicitly because you need to organize the data somewhere. If you create an index corresponds to a separate .db table internally. So every index is a separate distributed, sharded, replicated table. And it uses internal transactions. If you insert into a table that has indexes, it does an implicit transaction across the primary table and each of the indexes to give you consistency, atomicity, and all of the ACID guarantees. So that's what this thing says. All right, so an insert row will find the row, if you just do a simple row, belongs to a tablet, because every row or every primary key is owned by one tablet. So you go to that tablet and you do the insert. If you're doing a read, you just serve it right from there, because we have leader leases. And if you're doing an insert, it then replicates it to a majority, and then you're good to go. Right? So it's a standard thing. Note that in this example, we're looking at an operation that hits exactly one row, which is not the way it would be. I mean, you could have multiple rows being updated. You could have an update statement that moves a row from one tablet to another. You can have all of these complex scenarios, right? So we'll deal with that next, but this is just to give you an overview of what a single row operation looks like. Okay, so what trouble do we run into now, right? So now we've reached a spot of PostgreSQL where you can actually do single row operations with atomicity and consistency, ACID guarantees, high availability, all of that stuff. We still haven't touched distributed transactions or queries that span multiple nodes and tablets, right? So you just do a select star from the table. One issue that happens is you'll start your select star from, say, the first tablet, right? Like, which is a split of a group of rows. You'll go to the first guy and you'll start reading. And as you're reading, maybe people are inserting stuff into other tablets elsewhere, right? Now, your select star, should it return the new rows or not, right? So consistency in Postgres says it should not. You shouldn't see new rows. You should only see rows as of when you started the read, because the default isolation level in PostgreSQL is snapshot. So you should read from a snapshot of the database. But in order to do that, you need to find the time, the equivalent time on a different node, but the clocks can be off. That's really the problem that we're discussing in this section, right? And this is unlike Google Spanner, which uses TrueTime, which is a hardware-based service. It uses atomic clocks and GPS clocks in order to synchronize time across nodes, right? Now, obviously, the problem at hand is that you could have a begin transaction and update 2 rows, but the rows belong to different shards. The shards may live on different nodes. So the most complete version of the problem looks like that, right? So you want to make an update on one raft group and another update on another raft group, but you kind of have to do it atomically. So the time that all of these guys get written in and the data is visible should be some well-known notion of time. But how do you get all of these nodes to agree on time? So that's really the problem at hand, right? Which is what the famous TrueTime and atomic clock solves for Google Spanner. So you could use an atomic clock, right? Like what is an atomic clock? In simple words, atomic clocks are highly available and globally synchronized clock services, and they have very tight error bounds. So what Google Spanner says is if you're using their atomic clock, 2 nodes would never differ in time. The maximum skew between 2 nodes is going to be 7 milliseconds, right? So they kind of tuned it down to 7 milliseconds. And if you're saying, hey, I'm going to add about 7 milliseconds to every operation, it's kind of tolerable. That's okay, right? Like you can kind of wait it out. It's not too bad. But if any of you guys are asked to use atomic clocks, you're gonna be like, dude, I don't have atomic clocks. Like, get out of here. I can't really use this database, right? And physical clocks are not synchronized. If you use NTP, it's going to be that 7 milliseconds is going to become 150 to 200 milliseconds, right? So I don't think anybody would go for, let's wait for 200 milliseconds for the data to settle and become consistent. And then, so your minimum latency is 200 milliseconds. People will be like, dude, this is really not forget fast database. It's not even a usable database, right? So what do we do? So in Yugabyte, we use what are called hybrid logical clocks. So we reuse the NTP-based coarse synchronization. So you have the 150 to 200 millisecond synchronization window of NTP, and you add a logical clock to it, like a Lamport clock, to track causal chains, right? So if you do an operation which has the first operation, a transaction which has op1, op2, op3, it tracks that by using a counter, right? And all nodes keep exchanging this hybrid logical clock. When a node receives a hybrid logical time from another node, it will compare its physical time, and that node will bump up to the higher of the two physical times. If it has the higher time, it just ignores it. If it has the lower time, it bumps it up and resets the logical counter to 0, right? So we kind of start making these hybrid logical exchanges to kind of build a software-based atomic clock, which has good enough guarantees because we're able to figure out the causal chains inside. And as long as there are not too many conflicts, we're able to keep the conflict resolution to quite low. But if there are conflicts, obviously you want to be correct and not fast, right? And so by minimizing the window of conflicts and how many conflicts happen, you're able to get away with a lot better performance and a database that really has high performance in practice. Okay. Okay, so now that we've talked about a software-defined atomic clock, now we can come to the real problem, which is how do you do distributed transactions, right? Like, so I want to write, even after this clock, it's still not clear or easy to say, hey, if I write a piece of data across two different RAF groups, how do you make it instantly visible, right? That's the next problem. I agree that you can kind of now have a notion of time and you can make it agree across nodes, but how do you make this transaction atomic, right? So that's very similar to Google Spanner. It is based at a high level on two-phase commit and uses the hybrid logical clock as the MVCC time across nodes. The transaction design in Yugabyte is built to be scalable. So there is no single authority that issues timestamps. It's like Google Percolator. It's like Google Spanner, where it's distributed time synchronization. And that's because it's better for multi-region deployments. And some of the assumptions that we make over time, right? Like it works as is right now, but over time, we believe that global deployments are going to get more and more popular. So you'll want, multi-cloud, multi-region, hybrid, multi-zone, faraway geos, all of these will get more and more popular. And clock synchronization services in the cloud will get better over time. Like you already see Amazon offers a time sync service, as does Azure, and these will get better and better error bounds as these type of applications start to increase, right? So it's kind of based on that overall trend, but we still make it work for where we are today, right? Even with NTP. So it's just like a directional thought, right? Like where the world is headed versus where we are. And it is important to not use atomic clocks, so we use hybrid logical clocks instead. Okay, so some of the other things about the transaction design, there's no single point of failure or no bottleneck, which means there's no central authority that handles transactions, issues, timestamps, nothing like that. There is a distributed transaction status table. It is also replicated, distributed, highly available, and so on. It's a system table, and it tracks all of the active ongoing transactions. Every transaction that comes in has one of three states: pending, committed, or aborted, right? So pending means it's in progress and you don't know what to do with it. So you need to go and figure out, if you're doing another transaction and you encounter this, you need to figure out, am I going to conflict with this guy, right? If it's committed, you need to treat it like it's written. If it's aborted, just ignore it and move on, right? Those are the three states. And only committed transactions are world readable. A transaction obviously can see its own updates. So if I write something as a part of the transaction, I should be able to see it, which is what the transaction rules say, right? And the isolation level says I can see my own transactions. Others cannot see my transaction until it's committed, right? It kind of follows that paradigm. So a quick thing on isolation levels, which is if somebody else is doing a transaction, when should I conflict, right? Like this is what isolation level is all about. There's two very popular isolation levels, like serializable, which says, so here's a simple scenario, okay? So I want to deduct $10 from checking account, but only if the minimum balance across checking and savings is greater than say $100, right? So in order to do this, I need to read the savings, I need to read the checking, add them up. If it is greater than 100, then I deduct 10. Right? Now you can get into this or whatever amount. So let's say you have $105, right? And two people are doing this transaction. You could kind of get into the scenario where both people read these values and both of it looks like, oh, it's 105, and both decrease 10, and now you've decremented 10 two times, and now you're like, way below your limit. So whereas one should fail. So it's just that kind of stuff is avoided in serializable. In snapshot, so that's a read-write conflict, right? In that case, because you're reading one thing and not writing it, but it should conflict with something else that you're writing. A snapshot only detects write. There are a number of scenarios where you don't want the total balance. You're like, hey, the guy has enough money, just let him draw it. I don't care about this minimum balance kind of stuff. So in that case, you'll simply go look at what you read and what you write are kind of the same set. So in that case, snapshot performs much better. Postgres' default is snapshot. We do the same thing in Yugabyte. Postgres supports isolation, serializable isolation level. Yugabyte does the same thing. Okay, so with that, let's look quickly at the distributed transactions code path. So you have a transaction manager, which is any node that receives the transaction every node has a transaction manager. So you just hit any one node, it becomes the transaction manager. So the first thing is the client says, hey, update these two keys, right? K1 and K2. The transaction manager says, great, I'm going to do that. But first I need to record this transaction somewhere. So it goes and puts this into this transaction status tablet to say, hey, this transaction is in progress. This is the ID of the transaction, and this is the set of operations that it's doing, or just some information about it. Then the next step, by the way, these steps 1 and 2 are in practice squished, right? Which is an optimization. So Yugabyte pre-creates the transaction status record and just uses it on that node. So you can kind of avoid a lot of round trips for performance, but this is more the theoretical view of what are the things that happen, right? So in reality, you just take an existing transaction ID that was pre-created and you just continue. And so you just skip step 2 altogether, right? Because it's already replicated and ready to go. Then you write a provisional write. So notice that in this write, you write key equals value 1, but you say, hey, this is a part of a transaction. So don't just serve it, go figure out if the transaction state is committed or pending or aborted, right? So you kind of write this on every node that owns the row. So you're hitting multiple rows. And the result of this is you may hit some other transaction's provisional record, in which case you have a conflict that you have detected. And now you have to run your resolution rules. Hey, is this read, write, isolation levels? You have to put all of that stuff in and say, should I do something about this transaction or not? If you have to do something that because you conflict, today Yugabyte aborts one of these, but we're working on waiting and restarting these transactions implicitly. Today it does not. Today we just abort one of these two and assume the app layer will retry. Right? So anyway, so these are the transaction manager provisional rights. And then the next step after that is, now that you've gotten all your provisional rights, if you got it, then you just go and flip the transaction into the committed state. Right? So now everybody can read this transaction. Step 4's timestamp, the timestamp of when the transaction gets flipped to committed is the timestamp when everybody is now visible, because any read coming to anybody else will see this transaction bit and say, oh, wait a minute, it's a part of a transaction. Let me go figure out its state. It'll come to the transaction status table to read the state of the transaction. If it says pending, it's going to do conflict resolution. If it says committed, then it'll serve it as of that timestamp, right? So every query is acting as of some timestamp. So if the timestamp is below the commit point of the transaction, it'll look like pending. And if it is after or equal to or after, it looks like it's committed. Right? So then the next step is 2 things that happen. So if you look carefully here, there are 2 things. The first thing is number 5, where we respond to the client because everything is made durable. The second thing is asynchronously we flush. You don't want these provisional rights to stay forever, right? That means every time you do a read, you're going to do one more hop to find that the transaction is committed. And once the transaction is committed, it's not going anywhere. So we kind of flush in the background the value of this transaction being committed. So it'll erase this transaction ID bit from the transaction record, and the transaction is just updated to key 1 equals value 1, and the timestamp of commit is put in place. So now you have a real record there and you don't need to chase. So this is the way it keeps catching up, right? So, and this happens soon after the transaction is committed, responded to the client, but in the background. So for a little bit, you'll be doing this double hop chase, but pretty soon it'll kind of settle down. So that's all I had as far as the transaction piece. So I just wanted to go over like a couple of overview and then open it up for questions. There's one other section that might be interesting, which I have in my appendix, which maybe I can pull up and talk about, right? So our aim was to really build a powerful distributed SQL database. And, when we did the analysis, we felt that like, hey, Postgres is one of the most powerful databases out there as an RDBMS for like the query layer and its feature set and its open source nature. And Google's Spanner was one of the most advanced distributed OLTP storage architecture. So we said, like, let's marry the two and obviously build an open source database, equally open source database in Yugabyte. So would really encourage you folks to, check it out. We're seeing like Yugabyte's starting to grow, the community is growing, like a lot of interest, like I said, fully open source. We're like a lot of users starting to put more and more business critical applications. So there are folks that are doing over 300,000 transactions per second on top of Yugabyte today. So it's being used at reasonable scale for pretty massive workloads. These are numbers which when we were working at Facebook, these were some of the Facebook numbers that are like at this range, like 75 billion operations a day and so on. But now we're starting to see smaller companies hit these sizes as well, which shows the power of the cloud and the power of data today, right? Like it's just increased over the last few years. Obviously, Facebook's numbers have gone much higher, but this is not anything small by any yardstick. And again, we're an open source project, so we love your support. Like give us a star on GitHub, join our Slack community. A lot of interesting conversations about distributed SQL. I think the one thing I forgot to add in these slides is that we are hosting a distributed SQL summit in 2 weeks or so. It's mid-September. We have a lot of interesting speakers. It's a fully free online event, so it's like completely community driven. It's less even about Yugabyte. It's more about distributed SQL in general. So it has like academic people like thinking about how you build systems for distributed SQL systems. It's got like builders of databases talking about what are the trade-offs, why you do something or the other. It's got users, it's got ecosystem folks, like the keynote on day one is being given by Joe Beda, who was one of the original guys who created Kubernetes, and he's going to talk about, for example, how do you like do stateful workloads on top of Kubernetes, and why distributed SQL has a big place there. So these are some of the things, like for example, this is one talk. Another talk is by the Pinterest, and yet another one is by the Twitter folks on their distributed database evolution and why they're starting to look at distributed SQL and what was their path and what they're facing now. So it's just like very interesting exchange for people. So really encourage you folks to attend that as well. If the website is distributedsql.org, right? Like one word, distributedsql.org, that has the details, right? Yeah, I think happy to answer questions. And if we have time, I can go over how failover happens in a multi-zone deployment with a diagram, but I just wanted to like make sure we get enough time to answer questions.
Thanks so much, Karthik. That was really insightful. And thanks so much for taking out the time and doing it with us. I'll hand it over to Rajiv to do the Q&A. And Rajiv, if you can just start.
Yep. Thanks, Karthik, for the talk. So we have a few questions in the Q&A section.
Okay.
So Amir Nagri asks, what's the story behind the name Yugabyte?
Yeah, nice. I think Yug, as a lot of people from India might already know, represents a very long period of time. An epoch or an eon is like, it's really like millions of years, right? So in most of the databases in the big data era, most of the distributed databases like Cassandra and HBase, you mostly think about scale. So you think about megabyte, gigabyte, terabyte, petabyte, right? Here's a spin on the importance of how long data lives. So if you're doing operations like changing machine type or having failures in the cloud, you still have to preserve data. So Yugabyte is a play on data that lives forever, right? Like basically across the yugs.
So what's the largest known cluster of Yugabyte, which is basically deployed in production?
The largest known, I would say, is about 35 nodes. But note that these are like 32 core machines. So largest known cluster may mean less, like it's the aggregate power of what the clusters are doing. So like I said, we have multiple users who are in the hundreds of thousands of TPS transactions per second. So like that is concurrently happening. And some users that are trying to do a lot higher that are currently working with us. So we internally have tested it up to 100 node cluster. So we've done 100 nodes of 16 cores, but and at Facebook, we're pretty comfortable running 300, 400, 500 node clusters. So I think the architecture is such that it should easily scale to much larger clusters. But in practice today, in production for the mission critical workloads, we have about 32 to 35 node cluster, 32 cores each.
Okay. So Hafiz Kurnia asks, what are the pros and cons of using PostgreSQL plus Citus versus that of Yugabyte?
Yeah, good question. So the design is a little different. Citus is you can kind of think of Citus, the origin of Citus as being a shard manager on top of Postgres. So let's say you are doing manual sharding of your application, right? Like that means you identify a shard key and you kind of split the data set. Let's say you have user and user data, right? Like so every query will have the user ID. So you kind of split the data by the user ID and you put them on multiple PostgreSQLs. And each PostgreSQL, let's say, does asynchronous replication. And if anything fails, you'll kind of do the promotion of the slave and you lay out the system overall, right? So Citus makes that easy to accomplish. Now, what are the things you'll be giving up, right? Like, so some of the things that get harder to do are across these shards. If you want to do transactions, unique constraints, those kind of things get hard. So they put a coordinator node on top in order to facilitate that. But those would not be as scalable or as inherent to the database. So bottom line is, it is actually a group of databases put together, and the replication is native to Postgres. So on a failure, you will get some data loss because it's asynchronous replication underneath, right? So this is what I understand of Citus overall. The way Yugabyte is built is these nodes, right? 10 nodes, whatever it is, are a logical single unit. So you can do transactions, you can do, like, for example, let's say you don't want to do user ID, you want all the users ordered, right? For whatever reason, like maybe a different example is good, but you want all of these are not users, these are orders, right? And you keep getting orders and you want them lexicographically or numerically sorted, right? So you can do range queries. So give me everything between 10 and 100. So those type of things will get harder in a in a Citus-like system. But with Yugabyte, because it treats the 10 nodes as a logical unit, it does the sharding, splitting, and management in a different way. And so that's one difference. The second difference is on failures, you lose no data because the replication uses Raft and a whole different mechanism. So at a high level, Yugabyte reuses the upper half, Citus reuses the lower half of Postgres, right? Like in some manner of speaking. Postgres builds the shard layer and the management layer across the various nodes. Yugabyte builds the storage layer across that. So it's just the invert. And we think that, Citus was started before the cloud really took off. So we believe, for Google's paradigm, a more cloud native paradigm, Yugabyte is much closer to what we want to achieve. Thanks for the question. That's good.
Cool. So Satyajit asks, are all cross-region writes which happen on Yugabyte synchronous? And what kind of impact does it have on performance?
Yeah, that's a great question also. So Yugabyte, as I mentioned before, supports asynchronous replication also between clusters. So there's two possible ways you could deploy Yugabyte in a multi-region deployment. You can kind of have a synchronous cluster, like a stretched cluster across these multiple regions. In this case, let's say you have three regions, R1, R2, R3. Every write, irrespective of which region you write it to, will send the write to all three regions and wait for two regions to actually perform the write before acknowledging, right? So this means that your write latency is going to be, let's say you're always sending writes to region 1 to simplify, right? So then the write latency is minimum going to be the RPC distance between the minimum of R1, R2 and R1, R3, whichever is smaller. So that region and the nearest region, you need to take that round trip time latency, that will be your write latency. The advantage here is you get global consistency. You can read from the nearest data center, but you will sacrifice consistency. If you read as a consistent database, you will be, if you're reading from region 2, it will be that latency and so on. Now, asynchronous replication is you can deploy separate Yugabyte clusters in R1, R2, R3, which are like multi-zone or something, but which are strongly consistent, scalable, fault tolerant, all of that stuff. But these are independent clusters. Now you can start asynchronously replicating between these three clusters. So if you write a key equals 1 and the same key equals 2 in a different cluster, it will be like eventual consistency. So you will just do async replication based on a timestamp that was issued in each of those data centers. And the one with the higher timestamp will win. So last writer wins, it's called as the conflict resolution. But here you will relax your consistency, but your read and write latencies will be pretty low, right? So because each guy is only writing to that region. So we support both paradigms. Obviously for a spanner-like consistent deployment, there's laws of physics, so there's only so far, anybody can do to maintain consistency. Hopefully that answers the question. I think Satyajit is right.
Thanks for that. So Amitosh asks, how does the time sync and distributed transactions compare to that of CockroachDB?
Yeah, so at a high level, both the time synchronization for Cockroach and Yugabyte are pretty similar, I would say. I don't remember the details under the hood. Some of the things that we have done in order to make sure that the distributed system is really robust, and like Kyle Kingsbury from Jepson, he noted this when he tried to do this testing against us, is that Yugabyte uses the monotonic clock, or like what is called the hardware clock, not the OS time. So like when you type date or time, right, it gives you some time, but we don't use that. We actually go to the hardware and we use the number of ticks. The advantage of this approach is like, when NTP kicks in and readjusts time, or like, when you have time jumps because OS has become slow and freeze, like Yugabyte is much more immune to these. The second thing that we have done in Yugabyte is actually to use time deadlines instead of times, like actual time. So what that means is when you're replicating a leader lease at say 1 o'clock and you want a lease till 1:02, you will tell the next guy, hey, give me a 2-minute delta, not give me up to 1:02, because it's much easier to synchronize 2 minutes, which is really the clock drift speed, like the rate at which your clock runs, rather than the absolute time, right? So we do a lot of these type of things. I don't know what Cockroach does in this. So at a high level, it may be similar, but there will be real differences in the implementation, right? And again, it comes to the high performance, all of this starts to kick in. So.
Okay. So Suhendra asks, what kind of monitoring Yugabyte supports?
So Yugabyte has a ton of metrics that come out. So, as a commercial company, we have a commercial product called Yugabyte Platform, which exposes this monitoring, but the DB exposes Prometheus style consumable metrics. So you can take this data and put it into Prometheus. It exposes a native endpoint for that. In the commercial offering, which is the platform, these are already put into a Prometheus and visualized as graphs for you. So, and that's something you can totally build. It's like, it depends on, each customer wants a different kind of way of doing things, right? So, and if you want to integrate it into, say, your own environment, right? Let's say, like, for example, if assume Gojek were to use it and you want to put it in place, you probably already have a monitoring environment. You don't want to use a vanilla Prometheus or something. So you should be able to quickly write those adapters from a Prometheus-like endpoint to put it into whatever system. The actual metrics, there's like tons of metrics that are exposed, all the way from slow query, like whatever you would expect in a PostgreSQL, like PG stat statement style, like slow query logging, all of that stuff, all the way to very low level metrics like number of seeks at the docdb layer and the number of SS tables and so on and so forth.
Cool. So we'll take a couple of more questions. So Suhendra asks, do you have any CDC data ingestions from the like of Kafka Connect or direct replication from vanilla Postgres?
Yeah, so I think on the Kafka Connect, yes, I think the standard PostgreSQL sync, right, to Yugabyte should just work. This is something that we're actually working on qualifying. If somebody's interested and would like to work with us as a part of the community, we'd really love it. But otherwise, we're planning to do that. So it should just work as it is, because we're like really wire compatible with PostgreSQL, and a lot of Postgres applications have successfully moved over to Yugabyte. So that's number one. And the second question was, how do you replicate data from Postgres to Yugabyte? There's a number of migration tools out there that actually help you do live migration, including this one called Blitz, which actually helps do a CDC from Postgres. So as in, it'll move your data and bulk load your schema, but all of the incoming writes will get replicated in a transactional manner to Yugabyte, right? So both of those exist. So if any of those are of interest, like just reach out to us, join our Slack anywhere, and we'd love to help you out.
Okay. So we'll take one more question for the interest of time. So Eonk asks, I noted you specify replication factors and number of nodes on starting your cluster. What if I add a node at later point in time? How does it find and join the cluster? And how much time does the raft replication take to rebalance across the new nodes?
Yeah, this is a wonderful question. Again, a deep question. This is one of the places where we truly excel compared to any other database out there. So a few things, right? Because there is a system catalog. As long as the new node is introduced to the system catalog, like basically you will start the new node by saying, hey, here are the masters, or here is like a couple of nodes in the, like a few nodes in the cluster, and it talks to the masters in that cluster and joins that cluster and it expands, right? So at this point you have n-1 nodes with all of the tablets, and the nth node we just added with no tablet, right? So the way this works is internally the system will start moving tablets from all these other nodes into this node so as to load balance the entire cluster, and no one existing serving node is hammered to transfer data. So over time, one tablet at a time moves over. You'll find that the new node will be functional in a matter of seconds to minutes, depending on how big your data set is on the existing tablets. So as soon as the first tablet lands into the new node, it starts serving. The way this is done is every tablet's replication factor is one after the other increased from 3 to 4 by adding this new node for whichever tablet wants to move. So there are 3 replicas for a tablet. The new node is added, it becomes replication factor 4. And data gets moved over, the leadership is transferred, and then we drop an existing node, right? We retire one existing copy of the tablet. So we do this for every tablet across every node until the whole system gets rebalanced. It happens seamlessly in the background, but the effect that you'll see is that the new node is taking traffic really quickly, and the transfer is done by mostly copying compressed data files, right? Like, which is, I mean, you don't need to copy it, it does it internally, but it just copies data files.
Good. So in the interest of time, we'll stop taking questions now. So if there are more questions to Karthik, please reach out to him on Twitter and as well as the Yugabyte Slack community, which is basically available on the screen. So it's yugabyte.com/Slack. So I think you can join the Slack community and ask any questions related to Yugabyte or otherwise.
Okay.
Cool.
Awesome. And thanks a lot. Thanks, Rajiv. Thanks a lot. Really appreciate, like, you putting the whole thing together. Thanks, Ayush, also for organizing this. This is really good. And really enjoyed the questions. Thanks, everybody, for listening. Really had a good time. So
Thank you so much for taking out the time, Karthik. It's really early for you. We really appreciate you doing this. There were a lot more questions which we couldn't take, but I'm sure people would reach out to you personally and take those.
please do. Would love to hear, exactly as Rajiv said, like Twitter or our community Slack. Happy to answer on either. And a lot of people we're very active on Slack. So yeah.
Thanks so much. We'll end this.
Thank you, folks. Thanks
Thank
a
you,
lot. Have a good rest of the evening.
Thank you. Have a great day.